I thought this cute little picture might help take the sting out of having to take notes. So here's 6.4 continued. This first thing is something we've needed to talk about and we haven't had the time. So first off, I can use congruent triangles in this case and similar triangles to help me measure distances that are hard to measure directly. So if you look at this picture, it might be the Hoover Dam. I don't know, the book doesn't say exactly. But we could figure out this distance across this canyon here, this AC. Well, we can't figure it out directly. I can't take a tape measure from A to C because it's too wide of a canyon. And so I need a way to figure it out indirectly. And what we can do is we can use congruent triangles. So if you notice here that we have right angles in both triangles, and they've already, so this is what they would do. They would walk. They would be standing at point C, and they would put a stake in the ground, and they would walk a certain distance and put another stake in the ground at point B. And they would measure, just with a tape measure, the length of BC. And then they would keep walking along the edge of the canyon, that same distance, and then they'd put a new stake in the ground. So they were able to make CB and BD the same length, just by walking. And then surveyors and people that do things like this have the ability to be able to turn an exact right angle, and then they could walk a certain measurement here, and someone across the side of the canyon has put a stake in the ground here at A. So they have something that they are sighting for. Have you seen road construction workers? And these people have this sort of looks like a camera on a tripod, and they're using it somehow in road construction. Well, this is an application. So the person could now be standing at E, and he's going to keep walking toward E until he can sight through his tripod a line all the way so that he's able to see the stake at B and all the way across to that stake at A. So he's able to stand at E, look through the tripod, and see that B and A are lining up with where he is. And then he would put a stake in the ground right there at E. And he's created congruent triangles by doing so. This measurement that we're trying to find, we'll call that X. And then we know we have vertical angles that are equal. So these two triangles are congruent by angle side angle. And then the surveyor has absolutely no difficulty walking from E back to B and measuring that distance. It's not over a canyon. They can measure that, no problem. And then they would know that whatever that was, let's say it was 125 feet, then they would know, I think I'm looking at the wrong distance. They would be able to measure actually from D to E. Say that's 125 feet. Well, that side corresponds to this side that we're trying to find, our X. So we would be able to say that X was 125 feet. Just because my triangles would be congruent. So that's an idea that I've needed to talk to you about, and I keep running out of time. So to keep in line with this indirect measurement idea, measuring things that are difficult to measure directly, I can't use a meter stick to get the measurement or a tape measure, indirect measurement. There's another method that we might use, and then there's a third one that we're going to use in class one day. The second method is the shadow method. And this is the way it works. The sun is shining, and it casts proportional shadows on everything that's outside at that exact moment in time. And so there's this large tree outside, and you would love to know the height of this large tree, but it's just too tall. But it's casting a shadow on the ground that's maybe 40 feet. And you would love to know this tree's height. Well, the tip of the top of the tree to the top bottom of the shadow forms the side of the triangle, and this would be a right triangle. And then let's say you're standing outside at the very same time. We can measure your height, and you also are casting a shadow, maybe not that long. You're also casting a shadow. We can measure your shadow. And let's say you are 6 feet tall. Well, you are also standing perpendicularly to the ground. And if we create a side of a triangle from the top of your head to the tip of your shadow, then these two triangles are similar because the angle that the sun cast from the top of this figure down to the shadow, this angle right here is congruent to that angle right there. So these triangles are similar by angle. That means our sides are proportional. So we can do height over shadow if we would like for both of these figures. So we could do tree's height over tree's shadow equals the person's height over the person's shadow. And then we could cross multiply and divide by 5. And you know now the height of the tree. So that's the shadow method. The other method is called the mirror method. And we can also measure the height of that tree using the mirror method. And the mirror method is the one that we'll use in class. The way this works is you're standing outside and you've got a mirror in your hand. Well, no, let's see. Let's don't put it in your hand. You're standing outside and here's the ground. And we've got a mirror laying on the ground. Well, this is a fairly large mirror, but it doesn't have to be. So here's our mirror laying on the ground. And here you are. You're going to start walking back this way, looking at the center of the mirror. And you're going to walk back until you see the tip top of the tree in the center of the mirror. And then you stop. So you're no longer here. You're back here. So we will be able to measure the tree's height. We know your height. What were you, 6 foot a minute ago? We can measure from the center of the mirror to where you're standing. Let's say that's, I don't know, we'll say that's 40 feet. You are perpendicular to the ground. The tree is perpendicular to the ground. We can measure how far the tree is away from the center of the mirror also. I know it doesn't look like it, but let's say it's 100 feet. Now, these actually make similar triangles. From the top of the tree to the center of the mirror, to the top of your head to the center of the mirror. And the way mirrors work and light reflecting off of mirrors is this light hits the center of the mirror and bounces off and hits the top of or comes to your eyes. Or probably it goes the other way, actually. You look from your eyes to the center of the mirror, and in the center of the mirror, you see the top of the tree. So that angle right there that the mirror bounces off of, those two angles are the same. So my triangles are similar by angle again. And you can make up a proportion again. Tree's height over tree's distance equals your height over your distance. Cross multiply and solve. So these are just two methods of indirect measurement. We're going to try to do this mirror method in class. All right, and now we're going to finish up section 6.4. Oh, actually, I needed to do the air hockey problem for you. So we have a nice little diagram here. An air hockey player returns the puck to his opponent by bouncing the puck off the wall, as shown. from physics, the angle that the path of the puck makes with the wall are congruent. And that's just like we just talked about, the angle that our eyes made with the mirror to the top of the tree. How these angles right here were congruent. That's the same set of angles that we're talking about here. What is the distance d between the puck and the wall when the opponent returns it? So distance is always perpendicular. So the distance from the puck to the wall is this perpendicular distance. Well, we know how far away you were when you hit the puck to start with. You were 20 inches. These triangles are similar by angle, angle. Because you've got the two right angles and then the two angles that the puck makes with the wall. So you could do your distance from the wall over the puck's distance from the wall equals your distance. I've written over there. Your distance from where the puck hit the wall, the 26, over this distance here from where the puck hit the wall. They didn't tell us what that was. But if the whole thing is 66 and this part is 26, then that leaves 40 for this part, right? 26 plus 40 is 66. So that's what would go right there. So you cross multiply 20 by 40 and divide both sides by 26. And I got approximately 30.8. And they said, what is the distance? But they didn't tell us how to round, so 30.8 is great. Lastly, this is number 32. You can measure the width of the lake using a surveying technique, as shown in the diagram. So surveying, just like we talked about with the tripod and the measurement device on it, when we were talking about measuring the canyon. So we would be able to come up with these similar triangles to measure this distance across the lake. And we would do something over here to where we would, guess we would put a stake at W so we could see it across the lake, and then put a stake at X. And then I would walk a certain distance here, put a stake at Z, and then I would walk from Z toward Y, and I could measure that distance, just like I could measure from X to Z. And then in order to get parallel, let's see, what would I do? Somehow I'd be able, I'm not a surveyor, somehow I'd be able to sight from Y to some point over here that would have a congruent angle here because of those parallel lines. And I would just sight from Y through X to V, and I would be able to create these similar triangles. But they didn't ask us to explain how we would do it, which is a good thing, because I'm not quite sure about the ins and outs of it. They just want us to say, A part, what postulate or theorem can we use to show they're similar? Well, I didn't call them postulates or theorems, but it's the angle, angle, the side, 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 and the side, angle, side. These are postulates or theorems. So if these sides are parallel, I can do our Z and get our alternate interiors. So let me get rid of that. So we have our alternate interior angles. And then we have our vertical angles. So these sides are similar by angle, angle. To find the width of the lake, that's WX. So if they're similar, we can write a similarity statement. I'm going to say ZYX is similar to triangle W, remember we have to match things up, WVX, so ZY over WV, I'm going to pause it. Okay, so I just paused it while I went ahead and finished writing the extended proportion and plugging stuff in. And what they want us to find is WX, so this is the side we're looking for. Well, this ratio gives us our scale factor, and if we divide those both by 4, we get 2 over 26, so 1 over 13. I guess they divide by 8. One over 13 is our scale factor, so we'll set it equal to the ratio that has the WX in it. Cross multiply, and WX is 78. So it's 78 meters across the lake. And last, it says if XY is 10, so if this is 10 here, find VX. Well, again, I can take my scale factor, and I can use this ratio with the VX in it, cross multiply, and get 130. So these similarity statements are so powerful, and it doesn't take that long to write them. And then it really helps us out when we write our extended proportion and plug stuff in to find our scale factors.